Good morning, everyone. Okay, it's 8 o'clock. We only have 29 people here. So let's see who's here, who's not here. So all the good guys are here. And so because you guys are here early and you guys are good guy, hard studying guy, so I'm gonna give you one question you're probably gonna say on the exam. And whoever now here, uh, yesterday we're talking about step motor, right? The difference between step motor and servo motor. We're talking about one is open loop control, another one is closed loop control. And to driving those motor, you basically just putting some electrical pulses. So you send the pulse signal into those motor, and they will become, they call the discrete rotor movement. So the motor depends on how many those pulse signal you send in, they will rotate at a certain degree or certain step to make the rotor turning either clockwise or counterclockwise. So if you saw let's say a multiple choice question, they ask, they said, wherever the electrical pulse signal was sent into a certain type of motor to make the discrete rotor movement, it will be one of these. Depends on which one in the choice down there. We good? Oh, now we have more people. Did you guys just call them on the, what do you guys have? Discord? I'm sorry. I think I have a little bit of allergy or whatever, maybe cold. Yeah, it's such a hot weather. Shouldn't be cold. Sneeze a lot, and so might make a little bit of noise. I will try to mute myself before, but if I can hold myself and anything, I'm sorry to disturb you. Just give me a second. Okay, thanks. Second thing I'm going to show you here is I have something here. This is two metal wire made by different material, and I can plug this wire into a multimeter. The multimeter is set on the millivolt range. So now this junction is at the ambient temperature, like room temperature. So you raise 0 millivolts. If I use my hand to hold the terminal, my body temperature for sure going to be higher than the room temperature. So you can see is that millivolts reading on there, 0.4 millivolts. So I let my hand go. You're gonna wait a little bit because you have to wait for the temperature to drop to the room temperature. But you can see the voltage is dropping. Yes, this is the thermocouple. So you can see this thermocouple. It's very simple, just basically two different type of wire. You hook one terminal together. We have another terminal still open down here. So, but the thermocouple, when you change the temperature on this end, they only give you a very, very small voltage down there. So this voltage is basically too small to do anything. If you really want to use it, you got either if you try to measure the temperature, you're gonna put in certain type of the amplifier to make sure the voltage is bigger enough. Another one, I think I'm gonna show you down here. So this is a bunch of those thermocouple wire. We wire them in series. So we try to go from one to another, and when we wire them in series, now leave them open down here. The wire is too tight. So if I touching all those terminals, can you see the voltage is much higher? Before we only got a 0.3, 0.4 millivolts. Now I have a four together. It's a 1.3, 1.2 millivolts now. So if you're putting multiple thermocouple in series, you can generate a slightly higher voltage down there because each individual one is like an individual battery or individual voltage source. When you put them in series, the voltage generated going to be adding together. That's why when touching all the terminal together, I can get a kind of higher voltage down here. That makes sense? And also, when you're putting multiple thermocouple in series, it's called a Thermopiles. I believe that's the right spelling. So what if I told you this is important to know? You know what you're gonna do, right? Yes? No? I have another one. I'm not sure if this one work or not. This is I'm not sure if you can see clearly. No, you can't see it. What about here? Oh, now you can see it. Yeah, backwards. So this is a resistance temperature detector. It's directly, I think it's let me see. Yeah, I don't think I can make this thing work down here. But if you're looking on the label or specification down here, it's supposed to be 100 ohm resistance temperature detector. At 0 degree, the resistance is 100 ohms. At 50 degree, we're talking about Celsius, the resistance is going to be 119.397 ohms. And this whole module, I believe they need a source down in there. So they can give out 4 milliamp at the 32 degree or 0 degree Celsius, and they can give out 20 milliamp at 50 degree. So the range for this RTD is just 50 degree. when you're talking about the thermocouple, when you wire them, yes, you have to watch the polarity because if you, that's almost the same like if each of them, let's say put a 4 down here, it's 0.3 volts. We connect this one, we can get a 1.2 volts. But if we don't watch the polarity,
Yeah, can you focus your
oh, yeah. Yeah, so sometimes you got to speak up, it's better. While writing, I probably not watching the chat. So this one will give you 0 volts, right? Because the polarity, these two cancel each other, these two cancel each other. So when you connect the thermocouple in series, you have to watch the polarity. Okay, so another thing, by showing you those, you can see whether the voltage changing or the resistance changing is not a very big value. And that's why we said usually the sensor's output is not very useful. This is already a whole unit, so they might already have the amplifier and the signal conditioning, everything inside. That's why they can give you more different value of reading. But for a single thermocouple, when you heat up, I think maybe I heated up about at least I think 12 to 15 degree. The RTD usually is for measuring the temperature. So if you have a cooking appliance, they could use a RTD there to monitor the temperature. Depends on different RTD, they might have a different temperature range. And or if you're using industrial, you, let's say you have a car, you have to watching your engine's temperature, or you have to watching maybe a motor, a generator, everything's temperature. You could use RTD, or you could use thermocouple, depends on the temperature range, everything. Uh, yes, those could be they could use those thing, or they could have I have another piece down here. This is a one in industrial use. It's already pre-made, and this is a thermocouple. So I got this one is Alan. He gave it to me. It's he working in the beer brews before, so they have to watching each those brews tanks temperature, and they just thread this into the tank. They inside the tank they have another stainless steel tank. They have a they call the thermal well down there. So you thread this in there. They used to monitor the tank's temperature. And at the end here, you have the connection for the wire. The heat tracer is doing something else. Heat tracer is usually for heating the plumbing pipe. So if let's say Canada here, you those pipes subject to frozen, like especially in the parking lot, right? Because parking lots are open in the winter time, maybe the temperature drop too low, so your parking lot, those sprinkle pipe or domestic cold water pipe might be subject to frozen. That's where they use the heat trace cable. And even for lots of those, like if you are Asian or doesn't matter, you have those either water boiler, the new one, electrical water boiler or coffee maker, espresso machine. They all have those temperature sensor in there. So depends on the different range of temperature they have to measure. They're gonna use different type of those either RTDs or thermocouple or whatever the things they're using. Okay, so now we have 43, only 42 students. Anything from yesterday you guys have a problem, or you're all good? We can continue, move on. Yes, Steve, you are right. Encoder, yes, we're gonna talk about encoder today. So because like I said, this module 1 and 2 is the majority your exam questions came from here, and we have to cover them more slowly in more detail. Yes, we're going to talk about encoder today. I know when you do those online quizzes, some because they randomly pop up, so sometimes you see a question we haven't talking about, you're probably not going to be able to answer them. Okay, now we move on. So here we're talking about, yesterday we're talking about transmitter gave out standardized output. This 4 to 20 milliamp is very common, especially when the technology wasn't so, the new digital communication technology wasn't so popular. Lots of equipment uses 4 to 20 milliamps signal. So for the transmitter's standard output signal, usually if it's analog signal, they will either use 0 to 10 volts or 4 to 20 milliamps. That's usually for the electronic signal or electrical signal. Another one we're using is lots of industrial, they use a pneumatic signal. So pneumatic signal is the pressure. So 3 to 15 PSI. PSI means pounds per square inch. In module 3, we're going to talk about lots of pressure sensor, everything. 3 to 15 or 20 to 100 kilopascals. That also depends on if we're talking about in North America, or especially in the United States, they like to use imperial. If it's in Europe or somewhere else, we like to use the metric. So that's the two pretty common one. Okay. Then the digital communication protocol. There's a bunch of them down here. Like a heart is the highway addressable remote. I think transducer, foundation of the bus. This is a process field bus. I/O link is the Siemens use those type of they use them for the different manufacturers. Sometimes they come the standard communication signals. Active and passive transducer. Yesterday we kind of mentioned a little bit. The active transducer is they can generate energy output. So no external power is required. They give a sample down here, thermocouple, because the thermocouple can generate voltage. The digital, those one? Yes, so the newer one, the transmitter, they will actually can have a digital communication. Those things you probably not using them a lot because unless you're working in the industrial control section, but a common example I can give to you is some of you probably did a fire alarm system, right? So the old fire alarm system, like talking about maybe 20 or 30 years before, those one, it's all the analog device. So everything that time is an analog device. So even for the pull station, smoke detector, everything analog device. So when you wire them, you have to kind of wire them is each device will have two wire. You're putting them in a loop, one wire in, then this wire out to another wire, then this wire out to another wire, then this wire come back to here, make a splice, come back to here, make a splice, then go back. So that's the old way to wiring those analog device. But when you come to new one, if you install fire alarm system now, they call the addressable system. So they'll still have two wires, but you bring your wire in, wire down here, then you can keep going to next one, keep going to next one. So you don't have to bring one wire in. Oh, sorry. So this is old analog system. This is a new digital addressable system now. So the addressable system is from your fire alarm panel. They will talk to each device, use one of the communication protocols. They can talk to this one. They just have one busway. They will say, okay, I want to talk to the first device. They send the address out. The first device will be online. They will communicate with that. Then if they say, okay, I want to talk to the second device, other device will be quiet. Just the first one will be communication with the panel. And if something happened down there, this one, if there's a fire detector, either someone pull the pull station or the smoke detector or heat detector get activated, they will get on the bus. They will say, okay, I detect a fire alarm situation. I want to report to the panel. So when they send that message out, every other device going to be quiet. Let this device directly talk to the panel. So those are considered digital communication. For the active transducer and the passive transducer, is whether the device or the transducer going to generate energy. When we're talking about generate energy, is they can generate either a voltage or current. The thermocouple can generate a small voltage. That's why the thermocouple is considered active device. But like a RTD or string gauge, mostly those transducer or transmitters, they are just changing one of the electrical properties. They might change the resistance. Those are considered passive transducers. Here's some example of where transducer using in process control. So we have a process here. A pump is taking wherever the material from this tank and goes through to next process. But in here, because you want the production line to keep going, you have to make sure the material inside this tank they have a certain quantity in there. They meet the certain temperature in there. So for here, you have a temperature. Yes, John, you are right. So mostly the system you did it for now, if it's that's when I still doing it. Like the initiating device, those pull station, smoke detector, heat detector, those are all addressable. So you can connect the wire in parallel. But the time when I did them, those annunciation device like the bell, the horns, the strobe, those are still use the analog. So you need to use the wire to connect them. Usually for the analog device, you have to put the end of line resistor down there, so the system can check there's no open wiring or no short cross the wire down there. You're probably gonna learn more detail in the fire alarm when Jeff taught you guys those things. Okay, so we got a bunch of transducer here. We have a temperature transducer to make sure the material inside the tank reach the required temperature. We have a level transducer here to make sure there's enough liquid in here for the process to keep going. And also we have a flow transducer here to make sure the material come out from the tank is reaching the requirement for this process. And those transducers, they can have an electronic signal connect to either the indicator or recorder or the controller or all different kind of. We usually bring them to the center controller unit. We can have them recorded and we can know if we want to check them. Analog electronic signal used in industrial. Sometimes they use 1 to 5 volts. The way why they use 1 to 5 volts is they try to convert this 4 to 20 milliamp signal. For this 4 to 20 milliamp signal, if you put in 250 ohm resistor, 4 milliamps times 250 ohms give you 1 volts. 20 milliamp times 250 ohm resistor give you 5 volts. So basically down here, if this transmitter, the output is 4 to 20 milliamps, so the minimum current will be 4 milliamps, the maximum current will be 20 milliamps. And for this recorder or indicator or whatever, this type of signal receiver, if you put in a 250 ohm resistor down here, when this current come to here, you can give a voltage range between 1 to 5 volts. Then depends on that detailed voltage down here, it knows whatever the output current down here. Then this output current is in a linear relationship with whatever the input to this transmitter down here is. We're going to show you some example to do the calculation. So in your exam, you're going to have about 9 calculation questions. Those calculation is a majority is based on your input signal, your output signals. It all came from section module 2. So here's an example. Here's a steam generation plant. We supply the air and the fuel in there, and we're gonna creating heat to burning to turn this water into steam for a certain type of industrial process. But in here, we need a monitor certain thing. So first, for the steam, we have a pressure transmitter down here. This pressure transmitter, they're going to connect onto the output. They're going to give to the chart recorder. This is to recording the real time the pressure inside the system. So we want to keep a good recording. We want to know for 24 hours, 7 days a week, all the time, what is the pressure in here. Also, we have a data log down here, and we have an alarm monitor. So whatever the one they give to you is this chart recorder is taking 4 to 20 milliamp input, and they can use a 250 ohm resistor to converting that 4 to 20 milliamps into a voltage signal. When they converting in there from the voltage signal 1 to 5 volts, they will know what's the pressure down there. The data log and the alarm down here, they have a very high, super high input impedance. So if you're driving a current through those high input impedance, the supply probably not going to supply enough current for that. That's one thing. Second thing, for the high impedance, if you're driving a current through, the voltage will be too high. So they actually using external resistance to converting that 4 to 20 milliamp current signal into 1 to 5 volts voltage signal. There are no measurement device for the physical input. Here it is. We have a pressure sensor down here. The transmitter is including the sensor, the signal conditioning, and the output circuit. The physical input is from this pressure sensor down here. Yeah, when we're talking about transmitter, they have not only have a sensor, they also have a filter or signal conditioning. Then they have the output signal circuit. Yes. Yeah, we're using those 250 ohm resistor to change the 4 to 20 milliamps into 1 to 5 volts. Because we're giving out a current signal, So we want that current, if this one, the pressure sending out 4 milliamps, that 4 milliamp have to reach in each of the device, right? So all the device have to be wired in series, because series circuit, you only have a one current path, and everywhere the current will be the same. All those devices will record or monitor the steam pressure. The pressure transmitter will converting the pressure into a current signal. The resistor are utilized as a signal current to signal voltage transducer. So we use those resistors to converting this current signal become the voltage signal. Okay, so we're gonna do. So here the steam pressure gonna go into this pressure transmitter. Inside this pressure transmitter, first they will have some kind of sensor down here. It's kind of just like if it's a measuring temperature, we might use a RTD or thermocouple. But in here, they use a pressure sensor. We're going to talk about next module what type of pressure sensor is. Sorry. Then for that pressure, because they cannot give the pressure to those other equipment. And also this is a transmitter. So transmitter will output standardize the signal. The standardized signal here is 4 to 20 milliamps. So they have a filter, they have a output circuit. They will converting the input steam pressure into current signal between 4 to 20 milliamps. Then this one will go to this data recorder or register down here. And but this data recorder logger, they only can recording the voltage signal. So we put in a 250 ohm resistor here to converting this current into a voltage signal. Then at this side, we can measure this voltage. The voltage down here will be recorded by this data recorder. Can you still hear me?
Yes.
There's all different kind of recorder. Some are child recorder. Child recorder might be just give you a constantly some kind of lines to indicate. Data recorder might be just recording the detailed data. Because this data recorder, they have a very high input impedance. If they have let's say 1 mega ohm, your 4 milliamp go to 1 mega ohm, how many voltage you're going to get? So for this transmitter, they have an input steam pressure is between 200 kilopascals to 500 kilopascals. That's the steam pressure range. And the output, you have a 4 milliamps to 20 milliamps. So that's the output current range down here. When we do all those calculations, we only, and mostly for those one, we only ask you to do the linear calculation. So if this output or input is not linear, they don't have a linear relationship, we never gonna ask you to do the calculation. what they have here is they have a chat recorder, they have a data log down here, then they have an alarm monitor down here. So those three devices, they each have its own purpose down here. But for these two, they have a very high input impedance. That's why they use external resistance to converting that current signal into voltage signal. No, you don't. This is two different devices. They are not connected together. Yeah, those are three different devices. So for here, they give you some kind of example down here. They said the transmitter output relate to the steam input. Here's your current. Here is the steam pressure. At the 200 kPa, you have a 4 milliamps. That's the minimum. At the 500, you will have a 20 milliamps. So they give you some other values. At the 275, you can have 8 milliamps, 350, you can have 12, 425, at the 16. Any point on this line here, any point down here, they have a related pressure and a related current. So those are directly proportional. And the proportionality is constant. So inside this range down here, whatever the pressure signal we give the transmitter, we have a current signal come out. And on those three devices down there, whatever the current signal goes there, they will converting into a voltage signal down here. So 4 milliamp, we converting to 1 volts. 20 milliamp, we converting to 5 volts. Anything in between, they always converting into a voltage signal. They give you a table down here, but actually, this is for the device to recording those values. But for you, we will ask you to do the calculations. We give you the formula, we show you how to calculate them, but the important thing you have to remember or look at this picture down here is if I have a pressure at whatever the pressure down here, I will relate to a point on this line, and on this line, you will give me a proportional current signal down here. And with this proportional current signal, I can have the same proportional voltage signal down here. So that's how we're going to calculate the value at any of the pressure input. We will know what's the current output or what's data recorder or this data logger signal down here. We okay so far? I know you guys electrician, right? You like the calculation a lot because you did it for all 3 years and you never practice on the job. Just joking. So luckily on year 4, you don't have to do too much calculation. It's not like a year 1, 2, 3. You did a lot. You only need to do tiny little bit of calculation down here. So the advantage of the current signal down here, in your book, they also give you a list down there. I think, did you guys find those things on your book? So those thing is my type of book is on page 2-12. The current signal is less, they call it susceptible than the voltage signal for the electrical interference or noise. Because if you have those electrical interference on the wire usually have a resistance. When you have those ones, they will causing a voltage on the wire resistance. And it depends on the signal you're receiving down there. There might be a positive voltage or negative voltage created by the wire resistance. So then the final, when you reach the final equipment, the voltage signal gonna be get changed more easily than the current signal, because the current signal, the noise causing some kind of voltage on the wire, it's not gonna affect the current too much. Second one is the current signal can be transferred over long distance without losses. If you're using the voltage signal, the voltage drop on the wire, you have to subtract them from your input signal to get your output. But the current, they will creating the voltage drop on the wire. But if you keep the constant current after proper arrangement, the wire resistance is not going to affect the current in the system too much. Another good thing is because the minimum value is 4 milliamp, we are now using the 0 milliamp. So if somehow, let's say, one of the device doesn't work, become an open circuit, or one of the wire become broken, the final equipment, let's say if we have a wire open down here, will this one receive any current at all? There's gonna be no current, right? Because it's a series circuit. If you have an open circuit, there's gonna be no current flow. For that reason, if it didn't receive any current on the device, then you know either the wire is broken or some of the equipment is not working, have an open circuit. So that's where the live zero means. Because if you're using voltage signal, you receive 0 volts, you might not know if it's actually the input is 0 or if we have a damage in the circuit, there's an opening on the wire or anything. So the current signal, this is a big advantage, is they use 4 milliamp as the 0 point. The power supply usually is external to the transmitter. And once you have a power supply down here, and all the other device, they can working together with only one power supply. So major disadvantages, but everything, they always, you have an advantage, you will have a disadvantage. They will give you a live 0 signal. That's a good thing, because then we know if something go bad, the system will understand. But if any of the equipment is not working or the wire is broken, the entire system will not working. Because when you use a voltage signal, you can put all the devices in parallel. If one device doesn't work, that's fine. Other device still gonna work. But you using current signal, you put everything in series. If one device doesn't work, nothing gonna work. Also, the length of the wire, you still have to be taking into the consideration, because the power supply might not be, the power supply can only supply certain amount of equipment with certain length of the wire. So the first calculation example is down here. We have a tank. The tank have inside have a certain type of liquid for the industrial process, and we use an ultrasound level transmitter. This ultrasound level transmitter going to measure the liquid level inside the tank, and it's gonna be converting into a 4 to 20 milliamp current signal. We have a data logger, we have an alarm monitor. Same as we talking before, they have a very high input impedance, so we use 250 ohm resistor. We try to converting those 4 to 20 milliamp signal into 1 to 5 volts voltage signal. So we have two devices down here, each use a 250 ohm resistor. And the distance between the transmitter and those equipment, the data logger, the monitor, is 0.5 miles. So the distance is 0.5 mile, and how many wire we need to use? 2 wire, right? The wire resistance, because it's an industrial controlling wire, they are not gonna use very large size wire, they use smaller size wire. Those smaller size wire, we have a very high resistance. So the total resistance for 1 mile of wire is 300 ohms. Then the minimum voltage for this ultrasound transmitter requires 12 volts. So if you don't give it 12 volts, this ultrasound transmitter is not gonna working. And they choose a power supply at 24 volts. They ask you, is the system going to be working well? So now the total resistance in the circuit gonna be 1 mile of wire, give you 300 ohms. You have two devices, each need a 200 ohm resistor. So that's gonna be 250 times 2. They're gonna give you 500, 500 plus 300, 800 times 20 milliamps, equal to 16 volts. So for this transmitter to give out the maximum current, because 4 to 20 milliamps, right? They're gonna be used to indicate the liquid level inside the tank. If it want to give out a 20 milliamp signal, just for the wire and the device equipment, we need 16 volts. But your power supply only 24 volts, subtract 16 volts, you only have 8 volts left down there. And 8 volts is not gonna be able to driving this ultrasound level transmitter. So to make this thing work, the minimum voltage you have for the power supply should be 12 volts plus 16 volts, 28 volts minimum. How did you get 20 milliamps? For what's the standard for the current transmitter? Yeah, because your current transmitter have to be able to supply a current between 4 to 20 milliamps. So 20 milliamps is the maximum current. They need that value. We're okay for this one? That's if you want this thing to working properly, right? This transmitter need to be to supply a current of 20 milliamps. Oh no, the calculation we have, we 4 milliamp is the minimum current. If we using 4 milliamp here, it will work. But if we go back to here, we just looking, we consider this as the level of liquid in there. When the liquid level at the minimum, you want to give 4 milliamps. What if when the liquid level at the maximum, do you want to also tell those two devices, my liquid level is at the top, so I want to give out a 20 milliamp signal. But for this situation, will you be able to give out 20 milliamp? No, right? Yes, so for this type of thing, you have to use the maximum current to do the calculation to make sure the system will work. Okay, now we're gonna start showing you to do some calculations. Before that, we have to understand some basic things. One of the things is considered as a range. So range is defined as state minimum and the maximum measurement value. The relation between the input and output for the transmitter is wholly described as input and output range. So you have a temperature input. We have a temperature transmitter. This temperature transmitter, the input range is from 30 degree to 100 degree. So it can take the temperature between 30 to 100 anywhere. The output, we use a current output, standard current output 4 to 20 milliamp. And between this 4 to 20 milliamp and this 30 to 100 degree, they will have a linear relationship. They are directly proportional, so that's where we can have a straight line down here. The slope of the line gonna tell us what's the degree or what's the relationship between them. The minimum value of this range is called the zero value. The maximum value usually is also, they have a special name, they call the full scale value, but in here, we don't worry about full scale value too much. We care about the zero value a lot. So the input range, the zero value will be 30 degree. The full scale value is 100 degree. The output range, the zero value is 4 milliamp. The full scale is 20. Another idea they call it the span is on second page. The input and the output span. The span of the transmitter is the difference between the maximum and the minimum value down here. So the input span is 70 degree. The output span is 16 milliamps. So once we understand those two, we can start doing the calculation now. So for that, if we get all those, we can have anywhere, if I know the output signal, I will know the input temperature. Or if I have an input temperature, I know what the output current value will be. This is a more academic term. They call the static transfer function, the output equation. I don't require you to do this part. Something we want to show you here is the static transfer function is the relationship in the equation form. I will show you something. It's much easier for you to understand to do it. This formula, if you're good with if you're pretty good with the math, or you have a good math background, you can use this one to do your calculation. This formula is also in your book on page 2-15. But we found that most students come to our electrical trades, they are not so good with this formula. So we try to simplify something for you. So you saw the relationship down there. So for this example, here's my input, here's my output. It's let's say 30 degree, 100 degree, 4 milliamps, 20 milliamps. So we consider this relationship is linear. We start at 30, we give us 4 milliamps. We end at 100, give us 20 milliamps. So for any point on this line down here, if I have a value down here, the value in here, this is our x-axis, right? This is usually we call the y-axis. The relationship down here is this value for the temperature. So the temperature, x temperature, subtract this, because the minimum temperature is 30. So this value subtract 30 degree. That's this point on this line here. And this point on this line here, compared to the whole temperature range down here, so it will be 100 degree subtract 30 degree. We equal to, because they are the same line down here, so Y is our milliamps, subtract the minimum current is 4 milliamps, then over for the current is 20 milliamps, subtract 4 milliamps. So any point on this line down here, the relationship from this point subtract the we call the zero value, compared to the whole range, we equal to the current subtract the 0 value over the whole range. So that's the basic proportion between these two values. I know some of you guys will be able to do the transposing for this formula, but that's the basic idea. So to do a calculation down here, some of you might have difficulty to do the transposing. We're going to be converting this into, if you've been given this x value, you want to find the y value, you can do this. Your y milliamps going to equal to, because we want to find this value. So this value gonna be, we use 20 milliamps, subtract 4 milliamps over 100 degree, subtract 30 degree. This is, we move this one to the top. Then whatever the degree we know, subtract 30, we still have to add a 4 milliamps down here. So that is after the transposing. Or if they give you the y value for the current, they want you to find the x value, then all you have to do is, we can transposing this, it becomes 100 degree, subtract 30 degree, we just flip it. 20 milliamp, 4 milliamp, times this y milliamps, subtract 4 milliamps, add a 30 degree. So this is the basic transposing. We can converting them into this way. Okay, I gave you this is based on this question, but the book or this PowerPoint give you a comment. So all you have to do is using this bottom part. Your transmitter's output is the output span divided by input span times the input measurement, subtract input 0 value, then add output 0 values. Does this make sense? Good. So okay. So here's what I wrote down here. So this is I try to do is a step the transposing, but they give you, or the book give you a general formula, you can use it. And you will using this formula, like I said, you have about 9 calculation questions. I believe, if I remember right, you're going to use this formula for the at least 7 or 8 calculation questions. You're all going to use this formula. So this formula is very important to know. If you're good with transposing, you can using those. But if you're not too good, because I've been in BCIT for so many years, I notice most, I would say at least 2/3 students come to this trade school, you guys are not very good with transposing. So all you have to using is the last part, this formula. Now let's see. So can you find out at 40 degree? Oh yes, there's a lot of calculation we're gonna make you to do it. I believe I might have a working sheet. I will upload it onto the D2L. Can we try this one? At 40 degree, we're gonna be the output milliamps. Anyone give me an answer? Yeah, good. Eric, you did good. Did you guys get that answer? $6.28. Do I only have one student, Eric, in my class? Nobody else in my class? Joking. No, nobody is dumb in my class. I have confidence in you guys. If you put your mind to it, you're all gonna do good on this topic. Yeah, 6.28, 6.29. I take any of those answers. Anyone have difficulty want me to write down the calculation down here? So you have the formula, right? All we have to do is plug in there. So this is the one we try to find out. We have 20 milliamp, subtract 4 milliamps over 100 degree, subtract 30 degree. We know the temperature is 40 degree, subtract 30 degree, plus a 4 milliamp at the end. That will give us, you guys still able to see it, right? The 16 on top, the 17 at the bottom, 40 subtract 30 gave us a 10 plus 4. That would be, so 2.286 plus 4 will give us 6.286, or you can call 6.29 milliamps. That's good. So the next one you're going to calculate is 64 degree. So now you're going to try it at the 64 degree. what gonna be the output current? Good. Some people are really fast. You want me to write down for the second one? I gave you guys a little bit of time to say if you will be able to do it. Anyone else? Nobody give me the answer? Yeah, 11.77. That's your right answer. So 20 subtract 4, 100 subtract 30 times 64 subtract 30 plus 4. 16 over 17 times 34 plus 4. Easy cheesy.
Yep.
So once you know this, it depends on the range they give to you. We will say this: if I give you a current value, you're gonna use 17 divided by 16. But if we give you a temperature value, any of the temperature value in here, because that's your output span over your input span. So your output is 16 milliamp, input is 70 degrees. So for the same question, you're always going to be this value. Okay. Next one, 88 degree. If you get this 88 degree right, you can go for coffee. If you didn't get this 88 degree calculation right, I'm gonna be a slave driver. There's no coffee for you this morning. Gotta stay here to keep working until you can get this question right. Okay, so I will take both those answers, 17.25, 17.26. Anyone get those answers? We can take our early coffee. Let's take our coffee. We're back at now it's 9:38. So if you get the right answer, 17.257 milliamps or 17.26 milliamps, go for coffee. If you didn't get this right answer, you cannot go for coffee. You gotta stay here, keep working on, or draw a circle on your table. Put pen at here. I cannot use a ruler. Sorry. It's against, I don't want to get arrested by the police. Okay, let's have a coffee. Yeah, you can always ask me.
How long is the coffee break?
15 minutes. We come back at 9:38. Oh, I'm sorry. I got distracted by the email they sent to me. Okay, you guys back? Hello, can you guys hear me?
Yep.
Oh,
Yeah.
okay. Okay, so let's see. What if now for the same question, what if the output current is at 16 milliamps? Can you find the input temperature? Now we have different answers. We gotta be careful for the formula we're using down there, right? Yeah, 82.5 will be the right answer. So this time we're gonna go 100 subtract 30 over 20 subtract 4, 16 subtract 4 plus 30, 70 over 16 times 12 plus 30 equal to 82.5 degree. Come back to here. I like you to notice here, if this portion is temperature, the bottom portion is the temperature. If this portion is milliamps, the bottom portion is the milliamps. That makes sense? Because if we want to try to find the milliamps, the top is milliamp. This temperature and this temperature, they're gonna cancel each other out, left us with the milliamp only. If we want to find the temperature, the milliamp gonna get canceled out. We're gonna left with the temperature only. So do not make those type of mistake, okay? Should I give you another number to try? Let's say the output is output current is 10 milliamps. Find the temperature. Yeah, 56.25. That's the right answer. So anyone didn't get that 56.25? Or you don't want to tell me? You can tell me now. We're still gonna help you to do it. But if you don't tell me now, you let me find out on your exam, there will be some harsh consequence waiting for you. Okay, don't want to say anything. We're gonna keep going. You can try. The book also gave you a good example. All I have to suggest is use this, the last portion down here, but do not use that unless you are pretty good with your math down there. No, it's not a ruler. You're gonna cry after my exam. And you might have to come back to year 4 again. That's the bad consequence.
Hey, Jack.
Yes.
Because I was just looking at the book like 2-15 to, and then 2-16 to get that stuff, but that equation is just transmitter output equals output span
Over input span.
over input span.
Then your input measurement, subtract input 0 value.
Okay, that's great. Thank you.
Okay. Where you get lost? Or you just kind of falling asleep in my class because it's too boring?
No, that was me who wrote that. I'm just kind of confused about this, but I'm going to try and I'll do it afterwards. I won't hold anybody up.
Okay, we're going to give you more practice down here.
Okay, thank you.
Here's something more. Sometimes the question is going to be getting a bunch of more, what should I say, complicated. We might have those examples down here, but let's look at it here. A flow sensor connect to a transmitter, put out an analog signal to the system controller. The input to the controller is from 0 to 10 volts, corresponding to flow rate 0 to 500 liters per minute. The system controller converted the analog input signal to a digital value which is stored in an 8-bit memory register. So what we're talking about here, the 8-bit memory register is, do you guys remember in second year? No, third year. You learned a numbering system. Don't tell me you never learned that. In third year, electronics. One topic is the numbering system. We have a decimal. DE. Then we have an octal. We have a hex, decimal, and we also learn a binary, right? So in here, we octal, hexadecimal, maybe when you do the electronics, gonna have a review on there. We care about in our automatic control, we're gonna care about the binary because in a computer or in a storage device, everything is stored in binary. In binary, we know the binary only have two numbers, right? 1 and 0. If it's a 8-bit register, so which means you have 8 bits. So in each of those bits, you have 1, 2, 3, 4, 5, 6, 7, 8 bits. In each of bits, you can only store either a 1 or a 0. So the minimum number will be all is 0. That give you the number 0. The maximum number can store there is all is 1. When all is 1, the number we give you is 2 to the power of 8 subtract 1. Right? So that gave you the number 255. That's the maximum number. That makes sense? Yes? No?
Well, you're converting that number to binary.
This is will be in an 8-bit register. That's where the maximum number can stored in this 8-bit register.
Okay.
Why do I subtract 1? Can you converting this binary number to the decimal number? What's that going to be? Because the last number is all 0. The number you can have is 2 to the power of 8. But the minimum number is 0. That's why I subtract 1. So now let's look at this question down here. They give you 2 lines. One line is they give you an output of A. When the output of A, which means is A volts. At A volts, can you find out what's the flow rate? That's the first thing you're going to find out. Anyone? Yeah, 400 liter per minute. John, how can that be only 4? So it's you have 500 subtract 0 over 10 volts subtract 0, 8 volts. Now we give you 400 liter
Can you share your screen, please?
per minute. Right? Now the second part is we have a solution from 0 to 255. So we need to put converting this into a number down there. So you can use in 400 liter, doesn't matter, or you can use 8. Both way will work. The second part you're going to do is 255 subtract 0 over, let's say, 10 subtract 0 and 8 volts. Now we give you a number 204. Or you can use the 400 liter. 255 subtract 0, 500 subtract 0, 400 subtract 0 plus 0. You're also going to give you 204. Now, this will be the decimal number we're going to store in the, that will be the decimal number we're going to store it in here. Then we can find the last one. So that's B, it's 204. A is 400, B is 204. Now we're going to converting this 204 into a binary number and stored in this binary register. Do you still remember how to converting them? Yeah, 110, 1100. If you have this sharp calculator, all you have to do is we calculate 204. per second. Here above the divide button, it's a BIN, binary. No, we didn't do base A to base 10. It's an 8-bit register. So that 8-bit register is a binary. How we get a 208? We got 8 volts. So the total is 10 volts. And our register, the maximum number is 255. The minimum number is 0. So we can, it's kind of like we can use 0 to 10 volts, but any of those number, we can separate them into a 256 2 to 8-bit register. Is we can separate them into we should call, what's the name? We should call that into it's not called accuracy, it's called it's kind of like you have a voltage range between 0 to 10 volts, and you're using this 8-bit register. In 8-bit register, you can have 256 different numbers. So you're dividing that 0 to 10 volts into 256 portion. And then whatever the voltage down here, you can store in there, give you individual number. Yes. Justin Friend, do I answer your question? How do I get 204? Okay, and for converting binary number and the decimal number, you can always just use here's the binary number, have a B on top. If I want to convert into a decimal, press second, decimal. If I want to convert into hexadecimal, press second, hex. Want to convert into octal, second, octal, second, binary, second, decimal. Yeah, 8 volts is the measure on the input. So that's your A. A is we calculate 400. Transmitter A output is 8 volts. And this decimal number is the B, that's 204. C is 1100, 1100. That's the binary number to representing 204. Make sense? Yes? No? Yes. Yes, you will do one question. You have to converting them into find out maybe what's the decimal number in there or what's the binary number in there. Okay, if you get, can you do the calculation for the second one? Calculate what's the number D, what's the number E, what's the number F down there. So I saw Nathan gave me the answer. Anyone else? You guys just all falling asleep in my class? Too boring? My voice is now louder like Jeff. It's okay. As long as you're not falling asleep in my class, you are following me. Like I said, there are gonna be about 9 calculation questions, 50 questions. You can give up on those 9 questions, right? You still can get 82 if you get all other questions right. Okay, I'm gonna show you the answer down here. 0 to 500 volts into the transmitter, 0 to 10 volts out. To the register, you're gonna 8-bit register. Your output gonna between 0 to 255. So you can convert in directly from here to here. You don't need the center. That's totally fine. Or you can convert in anyway. Here's the calculation for this question.
Hey, Jack, would you mind flipping it back to that other page for just a sec? Thank you.
You're welcome. Good. Milan, you lost. Okay, between here, this portion, the conversion, can you do this? Between the voltage and the flow rate. That's using the formula we had before. Yes, no? Don't like to talk to me? You can type on there so I know if you get that part or not. Kind of. That's just like the one we did before, right? When we do the temperature and 4 to 20 milliamp, the question we did before. In here, your zero value is just going to be 0, 0. The one we did before is 30 to 100 and the 4 to 20 milliamp. It's the same formula we're using down here. You can see they're still using this formula. The output span is 500 subtract 0 down here. So instead of we did before is 100 degree to 30 degree, right? The voltage, because we have 8 volts, the voltage range is 0 to 10 volts instead of 4 to 20 milliamps. Still the same thing down here. The output span, input span. And we also add the 0 value. This one, the 0 value is 0. That's it. So if we can converting between this one, 8 volts to 400 liter, or 400 liter to 8 volts, like here, 200 liter, gonna give us 4 volts. If we get that part, the second part is we're talking about here, the 8-bit register. That's when you learned in third year about a binary. The binary, you have an 8-bit of a binary. That's your storage. Each storage, you can only put either 1 or 0 in there. So for this 8-bit, you can have a total 256 different number in there, but your minimum number is 0. So your maximum number is when you put in all the 1 in there, give you 255. So 0 to 255, it will be, you kind of can consider this is a different range. So you have a few different ranges there. One is 0 to 500 liter per minute. This is the flow rate. The output 0 to 10 volts. It's your voltage output for the transmitter. And the 0 to 255, you can consider this is your storage. Storage, yeah. Storage. think that's the right spelling. So those are all linear relationships. Yes, no? The only thing in here is you got to figure out how many, what's the number in there, can be in the storage. Okay. Maybe we do a few more calculation. You will get this part. Okay, so for this answer here, okay, this part just converting the decimal into binary. This part is converting the decimal into binary. This is in that storage, you can store 255 numbers in there. That's the maximum number you can put in there. This is the minimum number you can put in there. To put 8 volts in 10, 0 to 10, what number you should put inside there. Oh, so far the class becomes so quiet. How many people have a difficulty for this part? Yeah, that's why I hate this online thing, because I cannot see you guys' face. So I'm not sure if you get what I mean or not. Okay. To make your life easier, this is the main thing. So the flow rate and the output down here, like we did for the one before for the temperature. We're gonna do a few more other examples. That's the majority of the things you need to be able to do them. For the things stored in a register, that probably we encounter probably one question. So if you struggle with the register, we can go. You might need some practice, and we might need to do more questions. But the main thing is between the input and the output of the transmitter, you need to be able to calculate that. And that's the one formula we gave to you. Okay, we can do more examples. This one, before I think you do the calculation for this one, but yeah, we can do it. Operational amplifier have a voltage gain of 5, which means that the difference between the input, the output will be 5 times larger. That's the gain means. So the input for input 2 is 6. For input 1 here is -1. They ask you what's the output. So basically, this operational amplifier, these two signals add up, give you a value. Whatever the value down here, you times the gain, we give you the output value. So that's a pretty simple one. So the gain times the difference between the two input. Because this input 1 is -1, this is negative value. So input 2 subtract input 1, 6 subtract -1, give you 7. 5 times 7 equal to 35. I think you guys, if you in Harmonize, you didn't learn this operational amplifier. But in here, we just try to show you is if they talking about the input is whatever the value, they give you a value, they give you the gain, will you be able to calculate the output? Or if they give you the output, they tell you the gain, will you be able to calculate the input down there? So basically is your output equal to the input times the gain, or the input equal to the output divided by the gain. In non-harmonized program, you actually learn the operational amplifier. So that's why there's those type of calculation in there. This is they give you a certain transducer's specification. Here the percentage. So sometimes you they will tell you either the input or output is at a certain percentage. So for that percentage, you also need to be able to find out what's the maybe the current, maybe the voltage, or maybe the pressure value. Is this table make sense? At 0, let's say they use 4 to 20 milliamp, or they use 0 to 10 volts, or they use 3 to 15 psi.
Makes sense.
So you should be able to using any of them to do the calculation. So for here, right, if for 50%, it's basically 20 subtract 4 is 16. 16 times 50% give you 8. 8 plus 4 milliamp, that's the 0 value, give you 12. For here, it's a 15 subtract 3, give you 12. At 50%, 12 times 50% give you 6 psi. The 0 value is 3, so 6 plus 3 give you 9 psi. So those are, I think you have the PDF file for this PowerPoint. You can do a calculation based on those numbers. Let's say if you have whatever the percentage, you have a current, you can do that, or you can calculate a voltage, or you can even converting between those two numbers, or converting between those two numbers, converting between those numbers to make sure you can get all the value listed in this table. So that could be also a different working sheet if you want to working on them to do the practice. Now it's 12:29. We continue this afternoon. So please come back at 11:30. Should I be a slave driver? Let me see if I can. I don't think there's a working sheet on the D2L. I can upload a working sheet on there. Hold on a second. Let me find out first. Yeah, so yeah, later on, like module 1 and 2 is a big section. Later on is all smaller section. Module 5 is a little bit more, but 3, 4, 6, 7 is all very small. Okay, I will see you guys after lunch.